All right. So you guys got the topics in the email.
Yeah.
Cool. All right, cool. Exponentials and logarithms. Our last topic, as I just said, not on exam 4, which is next class, so Thursday. Exam 4 topics are in your email. They're posted on Blackboard. So review the homework topics. That's that. So this is it. Whatever we cover tonight, in addition to, I'll send out a review before the weekend. Probably while you're taking the test, I'll just formalize it and clean it up because I got all the ideas ready to go. But you'll have that study guide or study topics over the weekend, and I'll have some review practice problems too. So, cool. Ready to go? What do you guys know about exponentials already? Anything?
Sounds like it has to do with exponents.
It does have to do with exponents. True.
Doesn't the log help move stuff from an exponent down to like?
Yep, there's a property of logarithms which allows us to bring exponents down, so that's helpful. So we'll see that tonight for sure. So definitely a big thing about logarithms. So if you don't know much, maybe I can hook you with this. What's up, Mark? Suppose I'll give you $100 per day, just straight up $100 bill every day. It's pretty sweet. Wishful thinking, completely hypothetical. Day one, oops. So $1, day one, $2, day two, $3, day three, and so on. Or I'll give you a penny on day one, 2 pennies on day two, 4 pennies on day three. And what's going on here in part C? I think the doubling. So 8 pennies on day 4, 16 pennies on day 5, and so on. What are you going to choose? Supposing you like money. See? Why?
It grows exponentially.
What the heck does that mean?
It like doubles every single time.
Okay. That's true. So that's what an exponent is?
No. Oh yeah.
Yeah, it is. All right. Falling into all my traps. All right. So you said you didn't know what exponentials are, and I'm just messing around, like playing. But if you have a vibe that this is an exponential, it is an exponential pattern and relationship between day and amount. But I kind of tricked you in a way because I said, which one would you choose? Anyone want to choose anything else before I say anything? I'm only going to do this for 3 days. So there you go. Which one are you going to choose if I'm only going to do this for 3 days? Yeah, well, if I didn't finish my sentence, like that would go on, but I'm only going to do it for 3 days. So y'all choose C. Actually, I don't mind paying that much. I think I can afford that. So thank God I didn't choose A. I would have had a lot of money to pay. But in the long run, you guys think that C is going to be like if I was going to do this for, well, when would this be beneficial? That we would not get through all the content I need to, but it'd be really interesting to figure out when plan A is the best. So obviously, if I'm doing this for 1 day, plan A. 2 days, plan A. 3 days, plan A.
3 weeks for C to overtake B, and obviously 100 days.
3 weeks. 3
Over
weeks.
$1 million by the end.
You think so?
I
How much would it be?
I think he did that like 84,000.
So in a month, you said?
I think it's way more.
What's your gut kind of tell you? What's our
If I had to
guesses?
guess off the top of my head, I'd say 250.
Two-
Around
$250?
1,000.
250,000.
Just off the top of my head.
Anyone else? We do this for 30 days. Not that much. What do you think? Roughly.
80.
Quick estimate.
Roughly, probably maybe 10 grand
10 grand.
a month.
Anyone else? Over 1,000 for sure.
Yeah.
Yeah. Okay. Well, once you tell me how much we have, we can move on. Should I guide this a little bit so we keep moving? I wish we had a little more time. I love doing this question, especially because you guys are like walking right into what I normally would ask. Because my high school students are like just waiting for like every bit of instruction, but cool. So then I say, all right, well, what do you estimate? So anyone think more than 250,000? Just your gut feeling. Starting at a penny, 30 days you're doubling. $250,000. You think it's less?
Yeah.
So definitely a cap. Roman, you said about 10,000,
Maybe 60,000.
60,000. Okay. So in the tens of thousands, but 250,000 too much. All right. So the cleverness here is how you organize it. So we have day. We'll say day 1. What am I going to deposit into your account? A penny. So assuming you had nothing in this account, you'd have a penny. Day 2, I deposit 2 pennies. So you'd have 3 pennies. Day 3, you'd have 4. So that's 7. Day 4, you'd have 8 deposited. So that's 15. It's going slow. 16 would bring us to what? 31. I'll go one more time here. So 32 cents. So 63. Did I add wrong?
No, never mind.
You sure? No, seriously, I make this mistake all the
I
time.
thought you were doubling it for a second. No, you're not. That's good.
So I want to look at this. I'm going to give a little hint. How many times did we double this?
6 times.
No, right here at the beginning, the first deposit. Did I double anything?
Oh, 0.
So here's the cleverness. I didn't do any factors of 2. How many times did I double it? Once. On day 2, there's like 1 doubling factor. On day 3, all right, so check out these numbers. It's your penny, and it's been doubled twice. So 2 squared is obviously 4, 4 pennies, 4 cents. And if you double that again, someone's pulling out a calculator so they see something. What do you see? If this is day X. All right, yeah, so that you're answered. So the powers of 2 is not equal to the day number. It's exactly 1 less. Not more, right? See, so the day number is 4, but there's 3 doubling factors. All right, so there it is. That's how we can figure out what the deposit is. Before we do that on a calculator in just a second, and we'll see who's got the closest estimate. If anyone hits it within 10,000, you don't have to take the final, you get an A in the course. So that means you're all wrong. Because I wouldn't make that claim. Does anyone notice something about the total value? Just strictly pattern sense.
Always an odd number.
Okay, that's awesome. That's good to know.
Started with odd number, but
How else can we make that number?
double plus one.
What do you double plus one?
The day prior to the current day.
So if we take the prior day, let's start really easy. Double it would be 2 cents, and then add a penny will give you this total. See what I'm saying? So let's do a little work here. Let's make sure we got it all. Oops. On day 29, the deposit would be how many factors of 2? 28, 29, or 30? All right, cool. So we'll skip the total here. I don't really care. So day 30, that's the question. Here's what's getting deposit. Don't use a calculator yet. And the claim is we take this, double it, and subtract a penny. So this total will be 0, 2, minus a penny. All right, put that in.
100 plus one.
Add a penny. All right, calculator time. Let's see how much money you'd have in 30 days in that total. Two, a penny times 2 to the, I already forgot, 28. The deposit would be 29. Yeah, I got you. And then subtract a penny. 22,474,000. Oh, whoa, what? No, I was off. 53,687. No, 5 million. I thought it was in the 22 million. All right, $5 million. More than $5 million. So if you want to save money, start putting a penny away for a day and doubling it.
Still have to make that money deposit it.
Oh yeah, that's true too. That's true too. I thought it just happens like the tooth fairy when she comes and leaves money under my pillow. Damn, that would have been fun. Cool. All right, so that is our hook, our intro into an exponential function. So exponential functions, first, what are they? They have the form a times b to the x. So one thing to immediately notice, this is our input. It's an exponent. And the base is some constant. Well, a little bit more of that. It has to be greater than 0, meaning it has to be positive. I'll explain why in just another minute. And one other restriction, it can't be 1. And this right here is just a vertical stretch. So if I say this is truly what an exponential function is, and then this is just multiplying it, so that's just going to stretch it or shrink it so much. But just like we say y equals mx plus b is kind of like how we're first taught what a line is. This is like how our exponential function is like originally taught. So cool. Why can't be less than 0. So let's do an example. Suppose I say negative 2 to the x. There's nothing illegal about that. That is an equation, but it's not an exponential equation. Even though x is in an exponent, because the base is negative, from what I told you, it can't be. And this is really why. So if we input 0, what's the output? What's negative 2 to the 0?
1,
What's negative 2 to the first?
-2,
What's negative 2 squared?
4,
And what's negative 2 cubed?
8.
Negative 8. So there's this jumping between negative and positive. And in just a few more minutes, you're going to see everything else that is not negative does not jump between positive and negative. If it's not positive or negative, if it's not negative base, everything kind of fits a form with one other exclusion. What about if we had 1 to the x? That's a positive number. But what would this output? 1 every single time. And so graphically, it's just a line. It's actually just a constant function. So it doesn't fit into this family, right? So if we want to start to put things in families like parabolas, everything that's a U shape has an x squared, right? And then you can transform it or whatnot. This doesn't fit into what the exponential family looks like. So what does the exponential family look like? So if we take something like 2 to the x, or 3 to the x, or 3.5 to the x. And we look at these values. The whole numbers are pretty easy. 2 to the 0. 1, 2 to the first, 2 squared is 4, 3 squared is 9. I'll just kick this out a little bit. No, it's not 9. I said 3 squared, but it's 2 cubed, which is 8. And then 2 to the fourth would be 16. So there's that doubling factor, just like the pennies, except maybe these are dollars now. Oh, and by the way, see the number in front? It's an invisible 1. Earlier, it was a penny. So if there was a 0.1 here, we'd literally have the deposit anyways. We'd have the deposit function there. And for time's sake, if you put this on Desmos, you would see a curve like this. Actually, you'd see more. You'd see something over here in negative world. So let's talk those out. If these were negative exponents, -1, -2, -3, -4, what would happen to all of these values? They would reciprocate. That's what a negative exponent does. It just flips all these guys. So it'd be 1/2, 1/4, 1/8, 1/16. So all of these numbers that were originally getting really big are now getting smaller and smaller and smaller and smaller. And so you get a curve like this. All right. Same is true with 3. It wouldn't be identical to this graph, but in terms of like, if you stripped all the numbers off, if you put no numbers on it, you would just see a curve that's growing really big, fast, and smack them all with negatives. These become reciprocals, so they're also getting smaller and smaller and smaller. Like that. But I'm purposely not crossing 0 because I want you to extend your imagination. Think of a really big exponent, like a really big X, 100, 1,000, a billion, even bigger. Take 2 to that power, huge freaking number, huge number, and then reciprocate it. It's wicked, wicked small, probably smaller than anything that our mind can even fathom, but it's still something. It's still microscopically above the x-axis. We've had this conversation too many times. What do we call that? A line that the graph approaches. So every one of these has a horizontal asymptote at y equals 0. One of the most important things you'll want to know is that fact, that there's an asymptote at y equals 0. 3 halves, I'm going to think of as an improper fraction. So what is that? 7 halves. 3.5 is the same as 7 over 2. And the reason I like to think about that, I can actually work this a lot easier than I can 3.5. Meaning, all right, so to the 0 power, that's easy. To the first power, pretty easy. But 3.5 squared, I'm already kind of like shaking a little bit. I'm like, eh. But 7 halves squared, 49 fourths. And then I can approximate that and say, well, it's more than 12. I know it's more than 12. And then cubing this, all right, now 7 cubed. I think that's 243 over 8. And so now I know this is a number bigger than 30. So it has the same idea that it's getting big quick, and I'll just save myself with the time. And if we take big numbers and reciprocate them, they become small numbers. So it behaves like this. When your base is greater than 0, not 1. Let me rephrase that. When your base is strictly bigger than 1, this type of curve is called exponential growth. And so some closing remarks on exponential growth. We saw it when we had 0.01, the penny doubling a day. Things that grow exponentially, like in the real world, like when would you model something that is exponential? It starts off slow, it is increasing, and then at some point it just really takes off. So investments, when you hear that you should invest early as soon as you can, once you get into your real world jobs, start making some serious cash, you want to open up that investment account right away. Start pulling some out, because we're all going to go through this. I'm in this. I'm still here. Like, I'm not here, but I'm not at the point where it's like I see tremendous growth. But you're going to go through your 20s, your 30s, your 40s, your 50s, and then you're getting closer to retirement, and then they force you to start taking out money. This is why they force you to take out money, because they wouldn't be able to pay you at some point. So there's a lot of logistics in there. So I've been told, but it literally does grow exponentially. And anyways, I'll let that go. So investments for sure are something that can be modeled with exponential growth. Not perfectly, because obviously there's different factors that play, but overall, that's that. If we think, and I'm not going to do a bunch of examples, I'm just going to choose 1/2. So if I think about a positive number that's not 1, but it's not bigger than 1. So it's literally in between 0 and 1. Man, I feel like we've just seen this pattern. Yeah, with the 2s, but it was on the negative side. Now this is just on the other side of it. So this is going something like this way. And then obviously if we reciprocate all these, this would actually be 2. This would be the 4. This would be the 8. This would be the 16. And so our graph is going like this. And I'm going to step back before I tell us what this is. Exponential functions have a multiplier in front, might be an invisible 1, a base to an x. Biggest takeaway. Can't be a negative, because you wouldn't get this type of curve or this type of curve. You'd literally have a jump up and down. Doesn't fit in this family. Can't be 1. We already described that. Can't be 0 for the same reason as why it can't be 1. You'd always output 0. So if we make all those exclusions, you're either greater than 1, exponential growth, or you're in between 0 and 1, and we call this exponential decay. what's true about these functions. They have a domain of all real numbers. They have a range of not including 0 to infinity. So again, left to right, this graph's going on forever. And so is this one, and so is that one. There's your domain. Range, you're never outputting 0. I told you it's microscopically above 0, so you can be as close to 0 as you want, but not 0 itself, and then as big as you want, and the same with this one. They all have a horizontal asymptote at y equals 0. But what word or words can we use to describe exponential growth for decay? These graphs are doing what as you go larger into time? Goes up. So what, do you know a word that we call that? Starts with I? This is increasing. And these are decreasing. Calculus 1, after you get through something called limits, the next big thing you talk about is increasing and decreasing. So you use that word a lot. And when, trust me, you'll use it a real lot. And finding where it changes from increasing to decreasing, the point of inflection, you'll remember those words when you hear them soon. Anyways, so I'll let that go. Compounding interest. What's interest? I'm interested in card games. I like playing cards. I really do. Any poker players here? What type of poker? Yeah, that's like the popular one. Any other card games? Anyone play like Hilo Jack, pitch during like family gatherings? Uno? Hilo Jack. So the reason I don't have office hours on Tuesday nights, I may or may not be in a Hilo Jack league on Tuesday nights in North Providence, so, which is why I have to leave at 6:30. Compounding interest. No, not that type of interest. What's interest financially?
Percentage of the principal.
Ooh, another fancy word there. Percentage of a principal. So if you have like a bag of money and you give it to a bank or you put it in a stock market, and let's assume it's like safe, like it doesn't vary, like you're going to get, and let's just say 50%, that would be insane, right? So to make 50%, anyone in the world would just like die. So in today's world, when I meet with my investor, we try to find something where we move stuff around so that in 3 to 5 years, it's like a 6% compounding interest, 6 to 8. More than that, we're happy, but that's like a good goal and pretty consistent. So it varies, it fluctuates, but for the sake of this, let's just assume, and for sake of ease, you're definitely making 50% interest. So that means well, I'll get to this, but let's say you're going to make 50% in a year. So 1 year goes by, and now you have like your original deposit still there, called your principal, the initial amount, and now here's your interest. Cool. That's what interest is. Money that you can use for you. So when you save or you invest, pretty much like the profit you get is your interest. Similarly, this is what credit cards do, right? They have a bunch of money and you swipe your card and then you pay back that money plus a fee. So that's how interest works against you, unless you pay it off right on time. Right? So, and here's how compounding interest works. So let's go back to the 50% example per year. This is year 1. I got my principal and 50% of my money. Year 2, then my green bag of cash, my principal, still is going to give me another 50%. But now this thing starts to manifest. And so you get half from here. So this thing's like, oh. So in simple case, I put in $100. At year 1, I have 150. That's it. I could withdraw it, but if I leave it in there, year 2 comes by, I'm going to get another 50 from here. And then this 50 bucks now starts making $25. Year 3, you probably got the vibe of what's going on here. This manifests into 50%. Oh, and by the way, this guy has a little baby. So what's cool, this is what it means to be compounding. Like this amount is now starting to stack up. And then this will start to stack up and this will stack up. So just that's what compounding interest is. And that's how it works in a quick version. You do not need to memorize this formula. I would give this on the final. But this is how it's calculated. In the year 2025, this is not outdated. This is still how the amount, your final amount, is calculated. So as David said, this is called your principal, your initial deposit. R over here in the formula is the percent. Oops. As a decimal. So going back to the example, we put that green bag of money, whatever's in there, I used 100, we'd put 100 right there. And then I said 50%, you wouldn't put 50, you would put 0.5. You have to put it in its decimal form. N is called the compounding period. So in the example I used, you had to wait a year for you to get that first blue bag of money, that interest. But it turns out, so annually, N would be 1. But other types of investments could be semi-annually, N would be 2, or maybe quarterly. You get paid some interest, N would be 4, or daily, 365, maybe monthly, weekly. Monthly would be 12, weekly would be 52. And that's just like how long you have to wait to start to see it accrue. When do credit cards charge interest? Yeah, everyone says a month.
Day after the billing cycle.
Yeah, so they actually do per day. They have like a little weird scheme. As long as you pay it off, boom, you don't earn any. Like, so if you pay off this month, no interest at all. But if you don't, whatever's rolled over, it's not charged. It doesn't compound at the end of the month. They charge a % every single day. And you can pay your credit card. You don't have to wait for your bill, just an FYI. That's why you can just log in anytime and pay it. And if you are ever get yourself in a little bit of credit card thing, always throw money at it, like immediately, daily as you can, because it's going to calculate interest every single day. So you don't have to wait for the bill. If you just happen to have an extra $100 and you have some credit card debt, best way out of it is to throw it at it ASAP, right? So a lot of people don't know that. I'll stop talking about credit cards. I don't work for them. I hate them. I'm in credit card debt myself. So I get it. I'm still paying for my 20s, but I had a great 20s. And then T is time. Your time frame, all right? So I'd give you that formula and just be able to apply it. Very straightforward example. Suppose you have $1,000. You went to Twin River or Bally's, I guess it's called now. You're like, yo, I want to invest this. So you find a 3% semi-annually compounding interest account. How much would you have in, let's just say, 1 year? A, that's how much. That's what we want to figure out. 1,000, that's your principal. 1 plus 3%. Again, as a decimal, move the decimals point 2 places over, 0.03. And the fact that it's semi-annually, N is 2. And the formula says throw that 2 right here in your time frame of 1 right there. And that's meaningless, but pick up a calculator. Two times 1, I'm just going to spare myself there. And $30. Not bad. Yeah, it takes time to make money. But let's say you did this for 5 years, just out of curiosity. Oh, I can't copy and paste it. No. Okay, good.
Would that be 10? It's 5 years.
Oh yeah, I was gonna say that doesn't really seem super appropriate. Damn. Almost there. 1. Come on. All right, so N is 2 times 5. Yeah. So 3%, that's what it is. But get $160.54 profit. There's your interest. All right. Another common question. You might have children one day, so you want to have $50,000 to give to them towards college or whatever you want to do, or you just want $50,000 when they move out so you can party. You don't have to give it to them. Or not have, you want $50,000 and you're going to say, all right, they're going to move out in 20 years. Being optimistic. And so you go to a financial advisor. And again, in the year 2025, you find an account that's 6%, I don't know, quarterly. That'd be nice. Yep, probably not going to happen. Quarterlies, everything here is pretty realistic. You'd want $50,000. That's nice in 20 years. Seems realistic. 6% realistic. Quarterly, probably not going to happen. Annually, but I just want to use quarterly just for the sake of it. So the difference here is, here's our 50,000. This is what we want to find. Again, 0.06 over 4. And I forget what I used here, but 20 times our 4. So that exponent is really 80. And then we would just divide both sides of the equation by that value. So 5,000 divided by 1 plus point. Oh, yeah. 0.06 divided by 4 to the 80th power. One, 2, 3, 4 on top of 1 plus 0.06 quarterly 80th power. And so you'd have to have about almost 16,000, but exactly $15,194.51, just to be sure. No one has that right now, right? Just pocket change. Yeah, I wish. I don't even have that. If I had that, I'd be throwing out my credit card bill yesterday. Yeah, my credit card bill's over 15,000. Bad. All right. That's how this kind of works. That's how the compounding interest works, right? It's an exponential function for that reason. In a way, this is your base. It's complicated, but here's your base. We're going to know this. So here's what's varying. Here's your exponent, your input, and here's your initial amount. So in the way, it still has the value y equals a, b, and then this is just like a number times your exponent there, but at the end of the day, it's an exponent. So still fits an exponential function. Moving right along. Compounding continuously. Anyone hear this phrase before? Then start saving money. No, just kidding. Compounding continuously. So not every year, not every day, not every hour, not every second, not every half second or eighth of a second. That'd be cool, right? By the time you blink your eyes, you're already like getting some money. Quicker than that. And that's about as much as my human brain can fathom it. Like continuously, what the heck does that mean? Like it's literally rolling along? Yes. Like literally like live, it's growing. I don't know how to sell this. Formula slightly changes. And this number E is not a variable. It's literally, and I'm going to say this correctly, Euler, like O-I-L, Euler's number. Yeah, it's not Euler. Looks like Euler, but it's Euler's number. Mathematician Euler, credited for a lot of big things in mathematics, but at the same time, banking was around or becoming a thing in his lifetime, so he explored part of that and determined kind of just everything we explored so far. Okay, if you compounded once a year versus twice a year versus quarterly versus monthly, you could do this on your own, but it turns out the more you compound, if everything else stayed the same, so go back, if we said $100 at 50%, if you just did that yearly, that's a sweet deal. But if you did that semi-annually, it makes sense. It's going to work out better because that interest now has time in terms of a pitcher. The more time you're giving your interest to kind of grow, the better. So if you can let interest start growing every day or every minute, you're just going to have more money in the long run. And it turns out, whatever your instinct might be, you know, when I first heard the story, I was like, oh, so would it kind of be like a ton of money? Would it be like that penny example? But there's a limit to it. Like there's a ceiling to it. It's not. Like even if it compounds continuously, it's trapped. And that's what Euler kind of determined. So there's more to the story that needs a little bit calculus, but I'm just giving you enough hook here. E is a number. It's not a variable. It's about 2.71828. Wait, I wrote that completely wrong. 2.71828. Okay. And you can find it on most, or you can find it on all scientific calculators. On this particular guy, it's right here. 2.71828. It looks like it repeats, but literally the next digits, if we had any more room, doesn't. So that's that. R is still your rate expressed as a decimal. Biggest thing to notice though, it's in the place of an exponent. And just to show you do a little bit better, let's take the same example, 1,000, 3%, not semi-annually, but continuously. So 1,000, 3% continuous. That's the fastest you can get paid interest instantaneously. How much would you have in 1 year? A equals 1,000 times E to the 0.03 times 1. $1,030.45-ish cents. Is that more money than semi-annually? I forgot what our value was, but yes, it is. What was? Anyone remember what number that was? Anyone write it down? I'm not going to retype it. Just go back and watch the video if you care. But it is. It's not monumentally more, but it was more money. And that's what this number E is. I think that's it. That's not important for the test. That was kind of a hook into the lesson. Something that's fun, but definitely know what an exponential function is, know the restrictions, have an understanding why they're restricted that way. Definitely know if your base is strictly greater than 1. It's called exponential growth, has that type of behavior. If it's between 0 and 1, it's called exponential decay, has that type of behavior. Know the domain and range and the horizontal asymptote. Be able to apply this formula to find an amount or to find a principal. And same thing with this formula. It's literally just a manipulation. Next kind of section that's not going to be in the homework.
Will it be on the final?
Not this exactly, but I'm kind of lying to you. This is my hook. These things called what power functions. They're not real functions. They don't exist. This is another one of my silly stories. And they're not mine, Dr. James Tanton. What's the answer? 8, 4. Those aren't the same number. Fight. 8. 2 votes for 8. 3 votes for 8. 2 votes for 4 and 3 votes for 8. Orlando? 3. Tie. Oh, 4 is winning now. What's this one? 1 vote for 9. 4 again. You say 3. 4. 27. All right, so we have 9 changed to 27. So you're warm. Like, you are so warm because you're saying not just random numbers. I know the numbers, but I think we need more examples then. Power of, let's say, 2 that, oops. I'm talking. I'm not supposed to talk as I say these. This is 5. And this is -5. You got it?
Yeah.
So what's the answer there? Power to 16. You have to make the final decision.
So wait, one sec.
Oh, it's 4.
So I know. So I think it's 4.
because he said it. If it's wrong, I'm going to write no matter what you say, and we're just going to have to go with it. Okay.
So
Putting you on
to
the spot.
power of 2. That's the power of 2. That's the power. Yes, the power of 4 is 4.
Help me out before you tell me the final answer, because either we're going to run with what you say. Is there another way to write this equation
Yeah.
that would make sense?
Yeah.
How?
So you just put the number under the pow as the actual number, and then you put what's after the equal as the exponent. And yeah,
So these swap places.
I guess in a way, yeah.
Does that hold every single time? If we keep the 6 and swap these things, we
Yeah, looks
keep
like it.
the base and swap these things. This will be my last example. We'll just talk out the rest of them. So I will talk out the rest. Keep the 2, raise it to the 5th power. Yep. Keep the 2, raise it to the negative 5th power. We get a reciprocal. So we're going to keep the 2. Kind of think about what would make 16. 2 to the 8th? No. 2 to the 4th. Oh, I didn't give you a chance. So let's. All right. What's this guy? 3 to what is going to make 81?
Yeah, I said 3 for the jump.
Try that. So what's 3 times 3? 9. Another factor of 3.
Is that 9 times 9?
Oh, so we need 9 times 9. So how many 3s are over here that make 9? 2. And how many 3s are here? 3 squared. And 3 squared. I know, put him on the spot. But that's why I'm gonna miss this class. This is the most participation I get out of a 4 o'clock pre-cal class. So I'm gonna miss you guys. I've had fun. But yeah, and it turns out you just did logarithms. So no, what powers are not on the test, but logarithms are. What is log base b of x equal y?
B to the power of y plus x.
Correct. That's it. It's just an equivalent form of what an exponent is. You keep the base and you swap x and y. A logarithm is this thing. That thing is called an exponent. So here's the definition of a logarithm. From Wolfram Alpha, the best mathematical calculator there is. If you say define a logarithm is an exponent. One simple sentence. It's the definition of a logarithm. Whatever follows a logarithm is an exponent. That's it. Log base 2, let's just do a new example of 64. Without a calculator, you're thinking 2 to something has to make 64. And I don't know how well you are on your powers of 2, but even with a little bit of guessing and checking, it's not 1, but you just talk it out. 2 times 2 is 4, times 2 is 8, times 2 is 16. 32 to the 6th power. There's your answer. Right. What's this?
So what do we first want to make it log 2 64
Okay.
and then find what it equals?
Okay. So good. let's follow the order of operations, convert this to 64. And then what power of 2 makes 64? Oh, my bad. Why did I? Oh, man, that sucks. I totally screwed that up. I was so excited. I was like, you were walking right into it. I want to try that again. So we want to find 2 to the 6th power, which is 64.
Yeah.
And then what power of 2 makes 64? Oh, interesting. Oh, yeah, because we figured that out right up there. That one's easy, right? Is the answer 16? And by the way, you think for a minute. I'm gonna put what we had a minute ago, because I meant to do this, and I'm building something really quick tonight. We correctly said that this is 6, and then we had this discussion that we should find 2 to the 6, which would make 64, and then say, oh, that's 6. Obviously, I want us to see something, and you might already start be seeing it, but I'm not hearing it yet. So I like this path that we're on. So we would make this 16, but that's going to become 2. It's what? So your claim is that 2 to the 2 raised to the 72nd power is what? I don't know what it is. But your claim is it's 72. Can we confirm that it's 72? Let's think about its exponential form. 2 to something has to be 2 to the 72. By inspection, what the heck is frigging question mark? Is it 1? Is it -3? No, it has to be 72. Ah, good. So you found the first property of logarithms. And first is my first. It's not our textbook first, but it's how I like to teach this. I love logarithms. I can teach, like, I have this stuff. I love this section. Our first property is like, yo, if we have a log base 2, for instance, and a 2, they cancel out. A log base 4 with a 4 cancels out. And a log base 2 with a 2 cancels out. And this is absolutely true. Log of any base to a power is just n. And this is purposely called the inverse rule. What is inverse? It's the undoing. Moving right along tonight. Logarithms undo exponents, just like subtraction undoes addition, just like division undoes multiplication. I started tonight with exponentials. I said you have a base to a power. So if I said, oh, I have base 3, and this is what's varying, and I'm like, I'm going to raise it to the 3rd power. Okay. Then I say, oh, wait, I want to undo that. I want to get back my power again. I didn't mean to do 3. Like, I just want to undo that. Then you slap it inside a log base b, and you would get back your 3. So if you started like as an input of 3, and you raised it b to that power, but you want to undo it, you would undo it. So for the 4th time, logarithms are the inverses of exponentials. They undo exponentials. Now that we know how to undo, we can start solving equations. I want to get this by itself. Method 1. write it in its log form. Keep your base, make it a logarithm, and switch positions. So we'd have log 2. The 7 has to come over here. And the x has to go over there. And we're done. We solve for x. That's what algebra is. Get x by itself. We did. The answer is the base 2 logarithm of 7. Not all scientific calculators would do this, but this one does. Once, twice, 3 times. It's more than what whole number? It's between, let me rephrase that. What 2 whole numbers is this answer going to be between?
2 and 3.
Because 2 squared is 4, 2 cubed is 8, and we're trying to make 7. We're trying to raise 2 to a power to make 7. So it has to be between 2 and 3. And it is. About 2.807, whatever that is. Pretty cool. Method 2 is pretty much the same thing, but it's how it's taught. Rewrite in, not rewrite, my bad, is to literally just say, I'm going to take the log 2 of both sides of the equation. And then we use the inverse property that says, oh, if those are in agreement, they cancel out. Either way, that's how you solve for x. Now, if you're like, I don't have, like, cool, all making sense, this is mathematically awesome. But if you're like, I want to know the decimal approximation myself, but my calculator doesn't have that feature, give me a few more minutes. Your calculator will still get this. We just have to go a different way, but I don't want to like just tell you quite yet. Right now, I just want to say that's what a log is. We have the inverse rule or an inverse property, and we can solve some equations. Maybe not get the decimal. Maybe we can with the calculator. Desmos if you really needed it, but definitely in symbolic form, there it is. New page. Let me clean that up. All right, some more properties. I'm going to prove one of them. You're not accountable for the proof, but I still want to show it because we are a rigorous course. This will be the last rigorous thing I'm going to show this group of students because you're not going to remember it anyways, but you should definitely remember these formulas for Calc 1, 2, and 3. Any calc sequence, you're going to need your log properties. Since they have to be memorized in calculus, you have to memorize these. So the inverse property needs to be memorized. You got all this week, next Tuesday, but by the final, have your properties memorized. Inverse, this is called the product rule. Literally, when you have a multiply inside of a logarithm, we say it expands to a sum. Similarly, if you have a logarithm and inside of it you have a quotient, it expands to a difference. So when we take and go this way, it's called expanding. But there are times when we want to take the sum of two logarithms and condense. So you're definitely going to have a homework and at least one question that asks you to either expand or condense, or maybe two questions on the final. One that asks you to expand, one that asks you to condense. We're going to practice those in just a minute. I'm not going to add it to the tablet. So if you wanted to watch this on the video again, find it on someone else's YouTube page. But here's essentially the proof of the first one, and then we can just kind of like wave our hands on the other ones. But for instance, and I'm not going to do it super abstract, but the idea is this. Suppose I said log base 2 of, now I'm going to say 8, right? And I'll come back to this. For whatever reason, I don't know what this is. I do know. But I'm just going to say it's something. Oh, I'll call it X. My bad. I want to use X, right? I know what X is. It's 3. And then I'm going to take log base 2 of something else. Wicked simple. How about 2? And for whatever reason, I don't know what that is either. So I'm just going to assign a new variable to it. It can't be the same thing. Then I take this expression and rewrite it in its exponential form. So what is this in exponential form?
2x equals 8.
2 to the x equals 8. And what's this in its exponential form?
2 to the y equals 2.
2 to the y equals 2. And then I'm actually going to multiply the two equations. So 2 to the x times 2 to the y.
4 to the power of xy.
We'll come back to that. And then I have to multiply this side. Now I do know 2 times 8 is 16. But I'm going to leave it as 2 times 8. But it's 16. You said 4 to the what?
4 to the power of xy.
X plus y.
Oh, that's
We add the exponents. What's the base though? 4, 2, or something else? Just 2. Remember, this is really simple. 2 to the 5th times 2 to the 7th. Is it 4 to the 12th? No, you have 1, 2, 3, 4, 5 2s. 1, 2, 3, 4, 5, 6, 7 2s. Count the 2s. You have 12, not 4s. You have 12 factors of 2. So you just add the exponents. Okay. And this is 2 times 8. All right, I'm almost done with the proof. It's going to fall out right here. If I rewrite this in its log form now, take this expression. What's the base? This goes to this side. And what does that equal? X plus y, right? Doesn't that equal x plus y? The exponent. I wish I had a little more room. Check my work. If I take this expression and swap it into its logarithmic form, you keep the base and switch the exponent in the answer. What's x? Log base 2 of 8. And what's y? Log base 2 of 2. And I can switch the order, but notice this factor is right there, this factor is right there, and there's a plus in between them. So if I call this m and this n, there it is. The logarithm base 2 of m times n is the base 2 logarithm of m plus the base 2 logarithm of n. And I won't do it, but I'll just quickly do it. If these were all b's, There's the abstract proof. Formally, that's the proof of why that property holds. You're not accountable for it. Wanted to just show you a proof where this comes from. It really comes from exponent rules. We could talk out again with an example. And here's why I said I'm just going to do some hand waving. But it boils down to, if I have a quotient, then I'm not going to multiply. I'm actually going to divide. I'm going to do almost the same thing. But instead of multiplying the left and the right-hand sides, I'm going to divide. And when we divide this, we end up subtracting exponents. And so it just leads to the subtraction. Kind of cool. And it helps memorize them because I know my exponent rules. When we have the same base that are multiplying, you add the exponents. Since logarithms by Wolfram alpha are exponents, when we multiply, you can expand it to addition. And similarly, if you're subtracting exponents, I'll read it this way, then you really have a quotient going on there. That's how I remember them. This is also, you don't have to add this to your notes. What's another way I could write this expression? Basically, how else could I write repeated addition? Give me a way to condense that.
Log multiplication.
Okay. We just said if you're adding two logarithms with the same base, multiply these. So this comes to what?
M to the fourth.
Altogether. This would be m squared.
Yep.
Then you'd get another m, you'd have m cubed, and you'd have another m to the fourth. One way to think about this is use the rule I literally just formally proved. This would be m to the fourth. But an elementary school kid would say repeated addition is what?
Multiplication.
So you have 4 of those. And what if I had 5 of these? That would be 5, and that would be 5. What if I had, you get where I'm going with this? N of these, where you want n to be any number you want. Then you'd have n times that. There's my formal proof of the third property. Log base b of m raised to the n is n times log base b of m. And you mentioned it has something about bringing down the exponent. Here it is. Big takeaways. Inverse. You guys told me that. I didn't tell you. You told me that. I proved this for us because you have to have some background on that. But we kind of established this now together, our 4 rules. Right. Let's go back to something we did earlier. Oh, before I do. A logarithm with an invisible base. Because I chose 100. If it was 10, what would the answer to this be?
Oh,
And your calculator has this button. Every scientific calculator has a button. So you're claiming because I used 100, it's got to be 10. The invisible base has to be 10. And if that's true, what's this going to be as an answer? 10. So what power of the invisible 10 makes 100? Let's see. You knew it. It's called a common logarithm. And it has to do with John Napier, who, look him up. I wish I could talk longer. Mad cool story. But because we have 10 fingers and his discovery of taking multiplication problems and turning them into addition, but he didn't know he was doing logarithms. Cool story. Check it out. Back in the day, there wasn't calculators, and tedious multiplication, not bad, but multiplication could have been tedious for like scientists and mathematicians. And this guy didn't know he was doing logarithms, but he's like, I wish I could take a multiplication problem and turn it into an addition problem. And he actually figured out this thing called a slide ruler. So if you don't know any of this, it's mad chill. Really cool story. That was the calculator back in the day. If he had to multiply things, he was basically converting it to a form and then doing an addition question just by using a slider. And then he would switch it back. Really, really cool stuff. But you guys don't care that much. So a little cool story. The 10 is because we have 10 fingers, and that's what this guy figured out. Another French mathematician, and the fact that he's French plays into this story too, is credited for figuring out this. Anyone know what? Okay, so first of all, this is a logarithm. Anyone know what it's called? Natural log. That's strange because you said natural log, but it's ln. But I told you the guy who's credited for this is French, and a lot of us know Spanish, French, the noun comes before the adjective. In English, we put the adjective first. We say the natural logarithm, but not in other languages. So he called it the logarithm of El Natural or something like that. I don't know how to speak French. This probably sounds way more pretty than that too. Give it a little kiss. It's so beautiful. ln, natural log. So it's base E. We can confirm it with the calculator. Base 10. And so, by the way, the answer to this we already know was 2. And what's the answer to this? No calculator. 3. Inverse property. Base E with E cancels out. This is credited for an important fact. What's the answer to this then? It's the inverse property. E, but every single textbook and calc teachers will not say that way. They're just like, oh, make sure you know this fact. But it makes sense. We've built this entire story today. Right? Has to be that. All right, so now I can go back to this question and solve it yet another way. Method 1, rewrite it in its exponential log form. If you have a calculator that attacks it and you need a decimal approximation, wonderful. Method 2, take log base 2 of both sides. They led to the same thing. Again, you need a calculator though that does log base 2. Otherwise, mathematically you have a perfect answer, but in terms of decimal approximation, who the heck knows? But if anyone has a scientific calculator of any sort, we can take not just a base 2 logarithm of both sides, but we can take any logarithm, meaning I could take ln of both sides, or I can use common log of both sides. Now, can I cross these out? No, that's not the inverse property. This is base E, and that's base 2. They're not in agreement. The inverse property says you can cross them out if they're the same base. But what can I do here? Oh, you have an exponent. You're allowed to write that as a multiplier in front. So now we use the third property in that box, or like after the expanding, x kind of comes down as a multiplier. ln2 equals natural log of 7. And if we divide both sides by ln2, just to remind ourselves, I'd probably be quicker just to type it in myself. But that answer, the base 2 logarithm of 7, 2.807354922. Remember those digits. Actually, it'd be even better if you did it on your calculator, but if you don't have it out, natural log of 7 divided by natural log of 2. Same digits. It's the exact same answer. I took base 2 of both sides. I took ln of both sides. I could have taken base 10 of both sides. And the same thing would have come down. I just would have used the common log. The x would have come down, and then I would have to divide by common log. Oops. And you get, once again, the same freaking answer. And so the last property of logarithms says this. As a concrete example, 2 to the 7th, the base 2 logarithm of 7 is the same as the natural log of 7 divided by the natural log of 2, or the common log of 7 divided by the common log of 2. Now, suppose we were an alien planet. Did we do alien math at one day? Yeah, we did the whole thing. Suppose we had 7 fingers. What would John Napier use as the common log? Not base 10, but it would have been base 7. We would have done a base 7 logarithm of both sides. But let's just talk it out. Slap 2 to the x equals 7 with a base 7. The x would come down, and we just end up dividing by log base 7. Or what about base 13? Or what about any base you want?
Doesn't matter, because any number divided by number is still 1.
And this is called the change of base formula. Last formula to know. You can take any logarithm you want and change its base. This part goes on top. This part goes on bottom, no matter what base you use, whether it's E, 10, or any other number you want. This goes on top. So as a really quick example, suppose you needed really quickly in your calculator to find, and you don't have that feature, right? How do you figure it out? You change the base, either common log or natural log, because that's where your calculator. I'm just going to use natural log because it has less letters. Top divided by bottom. Put it in a calculator, you're good. Let's go back to something I said earlier. Expanding. I want to do expanding, condensing, and lastly, just the graph of what a logarithm looks like. And that's our course. A little potpourri, but in terms of assessment and the biggest things you need for calculus, we've hit it all. Expand.
Do you want us to try solve it?
No, I'm just taking a sip of soda because I pretty much talk nonstop there. I see two things. I see a lot of things, okay? But I definitely see a numerator on top of a denominator. So separate that. Separate that first. Break up. If you have a numerator and a denominator, the numerator comes first minus your denominator. Second conversation I want to have. Logarithms are exponents. And there's nothing wrong with writing square root of z. But as an exponent, what is the square root? 1/2. Remember, square roots are 1/2 powers, cube roots are 1/3 powers, and nth root is a 1/nth power. So for this homework and for exam purposes and for calculus, calculus has no issues with exponents, which is why we're learning this. Roots can be tedious. Exponents are a hell of a lot nicer. So anyways, I'll let it go. Get in the mindset of exponents. Roots, exponents. You're going to do it all the time in calculus. And you have to for this homework. Next, let's go back. Oh, I have a product. Let's expand the product. Products expand to sums. And arguably, I've expanded, but I want to add one more phrase. And I want all multiply, like I don't want any exponents inside the logarithm. So we're using all three rules. Well, there's an exponent of 1, but I'll let it slide. But this exponent of 3, bring it out as plus 3. And this 1/2 is the expanded version of that. Why? That does not look simpler. Again, I like to just tell you, in calculus, you're going to see a bunch of functions. And besides just tedious like skill work, there's reasons to do these things, but you're going to want to take this thing called derivative. I've mentioned that word a few times. And you could take this derivative as is, just like this, and it's quite fun. I enjoy it. It's sick. It's like a sick pleasure. It's really fun to do. But you have to work super carefully. There's things called, because there's a product, there's a product rule, there's a power rule, there's a quotient rule, then you got, I mean, you can do it in that form, and it's quite fun to do. But it ends up being like a lot of algebra mess. But it turns out you might not like this algebra here, but to do the derivative on this is 1 over x. This is 3 times 1 over y minus 1/2 1 over z. Done. Way simpler. That one I can't do. I could with pencil and paper, but I just did it in that form. So there's a reason why we do this too. You have to be able to expand logarithms. But there's also times to condense. Um, 2 log, I'll just use ln. Yeah, a little bit nasty. Okay. Let's start in our innermost parentheses. I see a plus. Can I call this b times c? No. This property says if your coefficient is 1 logarithm, and this property, either plus or minus, says if you are either adding or subtracting 1 logarithm, then you can condense. But if there's not a 1 in front, you're not in business. But that's okay. We know how to deal with this. We're going to put the 1/4 up there. And since I know I'm going to have to do this to condense it all down, let me just bring the 2 up there. So ln a squared minus, I'm going to keep this 3 in front until I condense this. So this is ln b times c to the 1/4. So the 1/4 goes up on c, and then this would be a 1, so I can multiply those two. I see subtraction, but this is cubed. That means all of this here has to be raised to the 3rd power. Ln a squared minus ln b cubed c to the 3/4. Both of these things are going to be raised to the 3rd power. So that's going to be 3, and that's going to be 3. And now 1 logarithm minus 1 logarithm. And if you put it back in a root, just to kind of recognize that you could do that, or you can leave it as 3/4. But if you were told to put it back in a root, or if it was a multiple choice option, you just want to be able to identify that that's the 4th root of c cubed there. Last but not least, I just barked at you for 90 minutes. You're done. We're done. But I can't let us go without talking about the graphs of logarithms, just so you have knowledge of them. What do we say about the base? It's always, nope, back to exponentials. What has to be true about a base for it to be an exponential function?
It has to be greater than 0, but not 1.
Can't be 1, it can't be 0. So there's one thing. But then there was 2 cases. Either the base was between 0 and 1 or greater than 1. So let's do a concrete example. Let's say the base was 2, like, I'll show you where I'm going with this. The quick way to not just tell you the answer, but to build the answer is, if I needed to know this thing's graph, I know it, and I want you to know its shape too. But before I do, let's go back to what we know. Convert this to its logarithmic form, exponential form, my bad. And this right here is an exponential function, but the x's and y's are just a little messed up. That's okay. I'll just put my -2, -1, 0, 1, 2, and 3 for that, and then build the x's. 2 to the -2, 1/4, 1/2, 1, 2, 4, 8. And then I'll plot this graph, and I'll use some knowledge. Will this ever be 0? No. But I can see that it's getting really, really close to 0. But this time, not as y values, as x values. So I'm getting really, really close to 0. I'll keep that in mind. 1/4. Now, as I start to move away from 0, I get 1/2 as an x, and then I'll put a -1. As I continue to move away from 0 this way, this graph is going like this. And we can continue to get closer to x, the y-axis actually, but like x is 0, we can get really, really close. These are just going to be more and more and more negative. What was once a horizontal asymptote is now a vertical asymptote. And a few things. I'm going to get it all in right on the friggin' money today. Exponentials, no matter growth or decay, had this domain and range. Exponentials and logarithms are inverses. Way earlier in this course, we said inverses mean domain and range switch. So now that I'm talking about logarithms, this is now going to become the domain, and that's going to become the range, which is exactly what we're looking at. You can get as close to 0 for an input as you want and go as large as you want. The previous range is now the domain. And the domain, the previous domain, which was all real numbers, is now your range. It's just switch places. Last but not least, for time's sake, I'm not going to build it, but we could. I would just do the same argument with a base 1/2 or 1/3. and you get a graph that you can get as close to x as you want, and it's just going to go downwards this way. So this is a quick sketch of something like a graph whose base was previously exponential decay. And in closing, my last two words, I'm a minute over, I apologize. This was exponential growth, which was an increasing graph. Its logarithm is still increasing. A little trick to memorizing it. This kind of stems from an exponential decay graph that was decreasing. This curve, don't cross the y-axis unless there was a shift or something, but I'm not even going to throw that at us. We've done enough. We could transform it. We're just done. But in the like this form, it's still a decay. It's still decreasing. Done.